So this is by far this is the most ideal surface for a radiator because you're dealing with by far the lowest environmental loading, radiation-wise. Okay, so if you wanted to figure out, given you wrap all 5 sides with MLI and then you have like an aluminum bar that comes up that you bolt to your thing that's dissipating heat, you can bolt it directly to the top surface.
Yeah.
You can compute what the temperature of your electronics are going to be now. And the reason for that is you do this analysis first. Okay, so you do so for the top surface you would say, all right, well I know we're dealing with IR loading, we're dealing with this case. So this is Earth IR, but it also relates to the atmosphere. The U factor is 1, we know the emissivity of about 0.8, we know the surface area at the top, and we can compute this via sigma t to the 4th. And we know that T is 230 Kelvin for the air. So, but we know the Q environment now on that surface. So then what you say is you come to this equation and you go, you come to this equation and you go, okay, we know the Q environment now. And we also know that we are getting rid of 15 watts. So we know that. So that Q is known. Okay. Sigma is a constant, A is known, emissivity is known. What's the only variable left? It's T. Okay, so let's say T comes out to be
330 Kelvin.
Just, yeah, sure. 330 Kelvin. Okay? That means that no matter what you do, like if you move all 15 watts, this surface will be 330 Kelvin. That's the way it goes. By default, that means your electronics are going to be warmer than 330 Kelvin, right? So what you do is you come up to here, and you have the Q. So this Q now, because it's conduction, and it's only conduction, it only deals with the heat that you're moving from the electronics. This doesn't take into account any of the external stuff. So now you say, okay, well now I'm trying to move 15 watts, and I know my K for aluminum, which, by the way, for aluminum is about 167 watts meters squared Kelvin.
Sounds right.
Okay, you know, and then the A over L ratio is going to be something that you're going to have to design and optimize, okay? And then you do temperature high minus temperature low. And you know that the electronics have to be operating at a warmer temperature than what the heat sink is. So you know that your temperature low is now 330 Kelvin because you did your radiation analysis, right? So now what's the only unknown? Well, you plug in some values for these, and you can find then what the temperature of your electronics are denoted by TH. Okay, and then you compare that TH to your 40 and your 50, and you see where those are. If your TH comes out to be, 60 degrees C, then you have to either make your area, you either have to make the cross-sectional area of the bar larger or the path length shorter, or both. All right, but that's how you take into account these environmental loads. You take a look at what's going on. You do a radiation analysis to know, take into account the environmental load and what I'm trying to dissipate. What's the temperature of the surface? And then once I've got the temperature of the surface, I can figure out what the temperature of my electronics are going to be. So that's how you back everything out.
So tangential note so let's say I've got a heat source here. This is my good, quote unquote, good radiator surface up here. So I'm going to have some heat coming up here, and some of it coming out here, and some of it coming here, and some of it coming out here, and some of it coming out here. Do I just treat this as basically a single point source radiator once it reaches the roof, or do I need to I guess I just treat this here plus here as my length. And just let's assume it's all leaving out this end here. I'll give you a pessimistic.
So if you want it to be super technical about it,
I'm not sure I do, but let's go. Let's keep going. Because
So if you want to be super technical about it, like what you would do is you would calculate. You would do this calculation as a series calculation.
Yeah.
Okay, so you would end up. I'm going to erase this if that's all right.
Yeah, that's good.
So what winds up happening is, just as a few side notes, your Ka over L is referred to as C, which is your conductance. Okay. And when you talk about what is an object's thermal resistance, like how much does it fight back to heat transfer, your R is simply 1 over C.
Yep.
Okay. So, and thermal resistors follow all the same principles as electronics resistors, where if you're in series, R total just equals R1 plus
Yep.
R2
And
plus
then-
dot, dot,
yeah.
dot. And then 1 over the inverses, right?
Yep.
Okay. So, when
Which
you
is
do
why
when-
you're doing these bunches of, yeah, that's why you're doing the bunch of.
Mhm. So when you're dealing with a bar that's like this, okay, and you have some source that's here, and you're dissipating to something that's up here, okay, so what you actually wind up having is you would compute the A over L, so you'd have like a resistor here to get to there, and then you come up to here,
I'll treat that as one.
you do a A over L for that, so you find the resistance there, okay? Which again, so you would have a resistance here, you'd have a resistance here, and then you'd come to here, you'd have a resistor there, and then you'd have a resistor to there. Okay. So you could do it that way. So the K is the same for all of these, but you have to be careful with your A's and your L's, right? So in this case, like here, when you've got something that is only like a partial length, then you're only dealing like with this as your A. Does that make sense?
Yeah, and that's something that we have a perfect thermal connection between these two elements, which we don't.
Which you're gonna have to, because like to get into stuff like that, you have to take a course on it. And then for this, right, you would end up dealing with this whole thing is your A, right? Because the whole thing is in contact, right? So this little piece would be your A, and then this whole thing up here would be your A. So then you could, if you really wanted to take all that into account, you have a series of resistors, and then you sum all of them together to get your R total. And then you can just take your R total value and plug it in here, right? Because your Ka over L is just 1 over R total. So then you can just rewrite your equation as Q equals 1 over R total delta T. Alright, so you can compute your series resistors. This is now known. You can grab that T from down there, and this is known. You can still find your electronics temperatures through that path. So, one thing that's important to be wary of is usually interfaces like this are very inefficient. You actually have a lot of losses at your interfaces.
Especially because this pump has a stainless steel housing.
So, interfaces tend to be nasty. One way to control that is you use thermal paste. Thermal paste actually makes a world of difference. It really does. It's very, very useful. So if you can get your hands on thermal paste, use it.
And is thermal paste going to boil off at float?
No.
Okay. I haven't checked the vapor pressures on it.
No. I mean, we're using it on Piper, so I think it depends on which one you get, which I guess would be a spec you would look up when you used it. But I mean, they use thermal paste for orbital spacecraft applications. So I can't imagine. Like, there's obviously thermal paste out there that does not boil off.
Space-based.
So, but that's how you do it. So my recommendation would be to MLI 5-year sides, leave the top surface no insulation,
and stick a big old
stick a big old rod up there. Yeah. And again, you're going to have to. So the other thing you can do, if you really want to play around with this, is let's see, 50C is what? 323 Kelvin?
Yep.
Okay, so let's just say this came up to 300. And you know that you want this to be 323 as a maximum. Now you're
already solved for that.
Now you're unknown as your A over L. And then you can just simply design, you see what I'm saying? Now you can design something that meets the A over L. So you can plug in different information and play around with it and manipulate it as you see fit. Because you have more than enough information to do that.
And you're pulling 300K from atmosphere? Or is that just an arbitrary example?
That was an arbitrary example number. That I was like, say you do the radiation analysis, it comes out to be 300. Then you take that number, you plug it in.
Can I see your math for Piper so that I have a second example to work off of? Do you have it in any sort of easily digestible or transmittable form?
I do not actually, because what I used to solve Piper was a system of 126 of these equations, and I pump it through an equation solver that doesn't give me the intermediate steps.
Okay.
It's just a generic systems equation solver. So, and the Piper math is like a billion times more complicated because
you got to get that one right.
Because you've got like surfaces radiating onto other surfaces, and then you've got boxes that have combined like subracks that not only radiate but they also have a conductive path. So there's an equilibrium that occurs. There's like the Piper example is like it's like 0, not even 0 to 60. It's like 0 to 2,000. Like so, and there's no intermediate steps. Otherwise, I'd be happy to walk you through it. But I know this is probably a ton to absorb, but does it make sense?
Makes sense,
Okay.
and I think I can pick my way back through it, especially if I refer to the video once in a while.
So
I'll probably write this out. I'm also wondering, just because we are down to the wire on this project time-wise, and our today, if I can take a shortcut on some of this stuff by, say, experimentally pulling. We run this thing in an incubator for an hour. I get my TL experimentally. I know my TH is a maximum, and if I can then kind of get a rough idea of the geometry, that'll work for me there. I don't know if that is cutting way too much out, or
I don't know how you would get a number for this that would be representative of what you'd see there.
Because we have atmosphere around it. Well, even if we do it in vacuum, it's an incubator. There's no way for a step to leave it, you know.
I mean, that calculation is not a difficult, right? You get the T from your radiation equation, so all you have to do is sit down for 20 minutes and literally you just run this. I mean, F is 1, this is 0.8, this is 15 by 15 centimeters, right? And this can be computed by multiplying two numbers together, and you know what that is then. So then you know your Q, and you know all this other stuff. I mean, this would probably take you 10 minutes to figure out what that T is. It's not a long process.
Right.
I mean, that literally is a 10-minute or less calculation to find that T. And then that becomes your TL for your conduction, for your analysis on what your thermal bar has to be, the bar where the heat transfers through, right?
Awesome. Thank you very much. I'll start chewing through it.
And then part of the reason why you're only using the 15 watts for the conduction is because if your sink is cooler than your source, then the heat's only flowing in one direction, so your Q environment's not backtracking and impinging on this. So you're only moving 15 watts because that's the direction you're interested in, so that's why you'll include the 15 and not the Q environment.
Oh, okay. That is where I wanted to kind of start, because I didn't want to have to worry about sort of any sort of not you would get alternating heat current or anything crazy like that.
So the radiation takes into account stuff coming from everywhere, whereas the conduction, right? There's no delta T here, right? It's just T to the 4th because you're just finding the temperature of the surface. Here, there's a delta T, which means directionality matters. Okay, and when you're moving from, if these were flipped, then this would be a negative, and so you'd have heat flowing from the surface into your electronics. Right? So, but because your sink is cooler than your source, the heat has to be flowing in that one direction. And how much heat is flowing in that direction? Like how much is coming from that source? 15 watts. That's like you don't talk about Q environment for this. Okay. I'm trying to think what else is useful here. Yeah, this is really it. I mean, you're gonna have to have one of your engineers basically just play with your A over L ratio is what it comes down to. So, because you're gonna find this in no time. You can set this to whatever you want to set it to. Let's say you want to say, I want it to be 35 degrees, just as to be safe. Then you set this for 35 degrees and you figure out what the A over L has to be. All right? So you can set the TH to whatever temperature your heart desires as long as it's warmer than TL.
Cool.
However, the closer you are to TL, the more and more difficult this is going to become. Okay. So because this is because the lower this gets, the more this term approaches 0. So then the higher multiplier you need to be able to match 15, right? So, it's really going to come down to just optimizing your A over L. And then once you have the A over L, you just machine a thing and you bolt it on with some thermal paste and you're done.
Right.
Yeah.
Thank you very much.
Crash course in satellite design.
I love it.